Recall, I wrote, energy is the ability to do work. And so far, I've given you two definitions of work. I've said this: work equals force times distance. But that only works, no pun intended, if the force, if the force is constant. If you have a changing force, ugh. And then I also told you that if you had a graph and it was a force versus distance graph, we said work was also the area under a graph between 2 points. That would be how much work it took to move an object from point A to point B. Work is what times what? Force times distance. It's also the area underneath a force versus distance graph. How do I know to use that one? They'll give you a force versus distance graph. It's usually fairly obvious. There's a third and better and more universal definition of work. In fact, this is the one that we use more and more in Physics 12. It's called the work-energy theorem. It's what relates work and energy together. It says this: work equals the change in potential plus the change in kinetic. And Max, when you asked me about number 7 from last day's homework, you'll notice I said, did it get any higher? No, so the change in potential was 0. How much work? They told me 600 joules. I said, that must be how much its kinetic energy changed by. It's a much more universal, it's a little tougher, but it's a much more universal definition of work. Now, what is the little triangle an abbreviation for? Change in. What's change in anything? Now, in Physics 12, all of you will instantly parrot back to me something important, but we're going to write it here. Change in always. Change in always. Change in always means final minus initial. So what's the change in potential energy? The final potential energy minus the initial potential energy. What's the change in kinetic energy? Kinetic energy final minus kinetic energy initial. Hey, what's change in voltage? Final voltage minus initial voltage. That's next year. What's change in magnetic field? Final magnetic field minus initial magnetic field. Trust me, it is. What's change in anything? Final minus initial. What's change in anything? One more time, because Justin didn't move his lips. What's change in anything? Okay. Why do I say that? Because every year I put a delta in front of something and kids freeze. But if I told them find the final amount, find the initial amount, and subtract it, they'd be fine. But I don't want to write all that. It's a lovely abbreviation. Change in is final minus initial. So you ready? Here we go. This is hopefully going to explain something to you about cycling. A cyclist weighs 65 kilograms. This bike weighs 7.2 kilograms. So first of all, what's the total mass here? 65 plus 7.2, 72.2? You okay with that, Thomas? Okay. How much work does it take for him to increase his speed from rest to 5 meters per second? Thomas, what's this question asking me to find? Read very carefully. Ah! I knew you'd get it. I knew you'd get it. What's it asking me to find? How much work? One more time. You're right. What's it asking me to find? How much work? Okay. Well, don't write this down. Work equals force, don't write this down, times distance. Read the question. Do you see a distance anywhere in the question? No. Is there a force? No. I mean, maybe I could calculate one. Yeah. Work is also the area under a graph. Look at the question. Did they give you a graph? Did they give you a graph? No. This is the process of elimination, Jordan. When they say find the work, I always start out by saying force times distance. No. Graph? No. Write this down. Work is the change in potential plus the change in kinetic. Is this question suggesting, remember, potential energy is mgh. If there's a change in height, there's a change in potential. Read the question. Are they suggesting any kind of hills or change in height? Okay, so we're going to make a little note here. We're going to assume that he's riding, or she's riding, so he's riding on level ground. So what's the change in potential energy? What's the change in potential energy going to be? 0, because the final and the initial will be the same. What's the change in kinetic? What's change in anything? So this is going to be KE final minus KE initial. Which is going to be a half mv final squared, take away a half mv initial squared. I think now it's plug and chug. A half 72.25 squared. Oh, what's his initial kinetic energy if he's starting from rest? Okay. That's how much work it takes for this cyclist to go from 0 to 5. What do you get? Come on. Okay, got something wonky going here. Exit without saving. Let's try that again. A half times 72.2 times 5 squared. Do you get 902.5? By the way, by how much did this person increase their speed? By how many meters per second? 5. B, by how much are they increasing their speed in part B? Oh, the answer is the same then. Or is it? Let's find out. Thomas, what do they want me to find in part B? The same thing as part A. Well, work equals force times no, they didn't give me a distance or a force. Work also equals the area under a force versus distance. Oh, no, they didn't give me a force versus distance graph. My new definition of work, Justin, this is the process you want to go through. My new definition of work, change in potential, change in kinetic. Although, Riley, I think we can safely assume the change in potential is nothing. Riley, what's change in anything? So this is going to be kinetic energy final minus kinetic energy initial. That's going to be a half mv final squared minus a half mv initial squared. It's going to be a half, 0.5, 72.2, 10 squared minus 0.5, 72.25 squared. Now, this is kind of weird because you're still only increasing by 5 meters per second. But how much work does it take now? What'd you get? What'd you get? 2,708. And Devin has a curious mind. He actually divided them, and he said, oh, it's 3 times as big. Is it 708 or 707.5 or something? It's exactly 3 times larger. Devin, what are we increasing in part C by how many meters per second? I wonder if that'll be 3 times. Well, let's find out. Now, I'm going to walk you through this one verbally. Work equals what times what, Max? Times, did they give me a force or a distance? I would scratch that out. Hey, work's also the area under a force versus distance. Did they give me a graph? No. In fact, work is going to be the change in potential plus the change in kinetic. What's the change in potential here, Max? Okay, you know what? Let's just jump straight to going work equals KE final minus KE initial. A half mv final squared minus a half mv initial squared, 0.5, 72.2, 15 squared minus 0.5, 72.2, 10 squared. Now again, this is the same 5 meter per second increase, but how many joules of work will this take? You get 4,512? Is that right? 4,513, I guess, if I want to round off properly. Did you divide there? I'm curious. What was our first answer? Oh, am I wrong?
Yeah. I just have to double check. I got 5,415.
Am I wrong, folks?
I got what you got.
Got what I got. I don't think I'm wrong. I think you're wrong. Sorry to say that. Don't check her. So now you have a good calculator. You got a 72.2. You got a 15, not a 20. And you got a 10, not a 5. Squareds. You got your squareds in place. And you got a different answer? Okay, hang on. We'll pause. You can hang on. Don't clear it. Did you clear it already? Yeah. My original was not. You know what? How many times bigger is that if I divide that by 902.5? This is 5 times bigger. First was 5 times bigger. But it's certainly not the same amount. Big deal. Actually, what this explains. How many of you ridden a bike before? Okay. This explains why it's fairly easy. It's not much work to get going medium speed. But once you're going medium speed, to double your speed, to increase by the same amount, takes way more work. Why? Because of those squareds. It's because of those squareds. Those squareds make it that much harder. Or, how many of you drive? Okay? This explains why you can't hold the gas pedal down on a car and just keep going faster and 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 faster. Because where's the energy coming from in a car? Okay, gasoline, the engine. Well, every time you want to increase your speed more, it takes way more energy to get that little bit of extra increase, and eventually there's a maximum point. There's a maximum point. This is why it's so much easier to walk somewhere and so much more tiring to try and run somewhere. It's not just that you're doing the work faster, generating a lot of power, but you're also just having to burn more energy to get up to the speed. Example 2. A rocket reaches a height of 340 meters when launched. If the top speed of the rocket is 85 meters per second, how much work does the rocket engine do on the rocket? Now, I mean, work equals force times distance. There is a height here, but I also see a speed here, which suggests there's some kinetic. I think my best bet here is to say work equals the change in potential plus the change in kinetic. Madison, in this question, is there a change in height? Yeah, so I'm going to ask you the same question. I'm going to phrase it differently, but I want the same answer. In this question, is there a change in potential energy? Yes. Yes. Kyle, in this question, is there a change in speed? In a rocket launch, does the speed change? Yes. I'm going to ask you the same question. I'm going to phrase it differently. I want the same answer, though. Is there a change in kinetic energy? Yeah, so I can't cross any of these out. Okay. Oh, hey, what's change in anything? Okay, so this is going to be mgh final minus mgh initial. There's my change in potential. We'll leave a bit of a space just to make it stand out. Plus a half mv final squared minus a half mv initial squared. Okay. M 0.15, G 9.8, final height 340 minus M 0.15. Oh, wait a minute. What's my initial height? So I could have gone 9.8, 0, or I could have just gone like that. Plus a half M 0.15. Final speed looks like it's 85 squared. What's the initial speed of a rocket when it's sitting on the platform? Okay, so I can cross that out too. Starts at rest. How much work? Plus a half mv squared. You get 1,042? Yeah? That's how much energy the rocket gains. That's how much work was done on the rocket. Where'd that energy come from? Where'd that energy come from? It's got to come from somewhere. Okay, that's all. That's why rockets need fuel. Okay, this is the physics of rocket science. Now, another place that bleeds energy off is as this rocket is traveling through the air, Thomas, it's bumping into air molecules, and since it's bumping into air molecules, each of those air molecules will take a bit of kinetic energy away because they're getting moved out of the way. So how do we design rockets? What shape are they all? We design them very, very aerodynamically for that. Why would you waste energy bumping air molecules away? You want as much energy to go into height. You want as much energy to go into height. And this leads us to the classic rocket conundrum. What if you wanted it to go higher? I would need to add more what? Fuel. But when I add more fuel, what automatically goes up? Mass. Oh. So this number gets bigger. So I need to add a little bit more fuel to take care of the mass. Oh, but did I just add more fuel? So what? Okay. You get an equation that's constantly changing. You need calculus to solve it, but it is a classic rocket equation that says, okay, what's my break-even point where I have enough fuel to take into account any of my rocket mass and any of the extra mass of the fuel that I kept adding? There is a magic point that you can find. Example 3. A car is traveling at 35 meters per second. That's about freeway speed, give or take. Oscar, what does A want me to find? Oh, work. Okay. So, of course, I would say to myself, work equals force, don't write this down, times, do you see a force or a distance anywhere in this question? It's also the area under a force versus distance graph. Did they give you a graph? Oh, so we're going to use our new and improved definition of work. It's the change in potential plus the change in kinetic. You okay with that, Justin? If you look at this question, Oscar, does it suggest a hill anywhere in this question? No? So what's my change in potential? I think we're on level ground. Let's assume that our change in potential is what? 0. Change in kinetic, what's change in anything? Oh, so this is going to be kinetic energy final minus kinetic energy initial. Now remember, kinetic energy is the energy of motion. By the way, you notice the birds are still going, right? Still motion. Kinetic energy is the energy of motion. So, are any of those 0? Are we ever stopped? Final or initial? What's that negative? We're going to get a negative answer because we're losing energy. The car has to lose energy to come to a stop. Work is going to be negative a half mv initial squared. Negative 0.5, 1250, 35 squared. How much energy must this car lose? Because the energy, again, the energy's got to come from somewhere and got to go somewhere. So if a car has energy, kinetic energy, it has to get rid of that somehow. Otherwise, it's not going to stop. You get negative 706, that there, negative 65625. I'll go negative 600 and, negative 766. I'll go 000 joules. It's got to lose a lot of energy. B. Cade, what's B want me to find? What? Huh? Oh. What did we just find in part A, Cade? Work. Can you think of an equation that has work and force in it? Now we're going to bring out that equation. What did you say we're being asked to find here? Can you get the F by itself? Okay, so the force required for this to work, no pun intended, is going to be the work divided by the distance we need to stop. It's going to be, this time I'll write down the whole number, negative 765,625, negative 765,625 divided by 85. And I get negative 9,010, roughly. It says 82, Mr. Dueck? Well, that was dumb. And what else is dumb is my pen magically just stopped. Don't tell me we're going to do this again. And just like that, we're back. So instead of 85, how about 82, Mr. Dueck? Well, that's irritating. Maybe I can get it back. Let's see. It was that divided by 82. How about negative 93367? I'll go, how about negative 9340? Units, it's a force. Newtons. What's the negative telling me? It's telling me the force has to be in the opposite direction of what? Of the car moving, yeah. So that, because force is a vector, and I am getting kind of a vector. It's saying, look, if you're, it has to be in the opposite direction of the distance, really, because work is force times distance. What if you had more distance to stop? What if you had a longer distance to stop? Would the force required be bigger, smaller, or the same? If this, I heard it. Someone said it. Smaller. What this is saying is, if you have more, and this is obvious to anybody who drives, but no, it's saying if you have longer distance, you don't need to hit the brakes so hard. But this is the physics of why that's the case. And again, anybody who's driven has figured that out. Oh, if I start slowing down sooner, if I take a longer time, I can tap the brakes instead of hammer the brakes. But this is why. This is why. What force is helping you stop? Now, I said brakes, but really, what's the force that brings a car to a stop? Friction. That's why it's so tough to stop on ice. So, Devin, what's part C you want me to find? So if you have 82 meters to stop, and your car is traveling 35 meters per second, what's the minimum mu? What's mu? I don't know what's mu with you. What's the minimum coefficient of friction? Devin, what did we just find in part B? Which force?
Friction.
Friction. You know what? Friction equals what times what, Devin? I don't know the norm. Oh, hang on. We'll come back to that in a second. What did you say this question wants me to find? Mu. How would I get the mu by itself? So mu is going to be friction divided by the normal force. And Justin, friction is going to be, now I'm going to ditch the negative because mu I know is positive. It's just a number. It's a ratio. So I'm going to ignore the negative. I'm going to write 9336.9. 93, but I'll use my answer button. What is the normal force? Can you visualize the free body diagram? I think the normal force here would be mg. Yeah? It's going to be this divided by, what did I say the mass was? 1250 times 9.8. There's more than one number in the bottom. I put it in brackets. I forgot to cancel the negative on my answer, so I'm going to get a negative answer. I'm just going to ignore the negative. I need a minimum coefficient. Ooh. I need pretty sticky tires and pretty sticky pavement for this to work. 0.76. What were the units for mu? Newtons? No, mu's not a full. Oh, what were the units? It's actually newtons divided by newtons. The units cancel. Mu has no units. It's just a ratio. Okay. Now, anybody here drive a hybrid? Or parents drive a hybrid, a Prius? So before you turn the page, this is very cool. I've told you that for a car to stop, it has to somehow get rid of its kinetic energy. So the Tesla and the Prius, what they do when you hit the brakes, I kid you not, friction isn't what's bringing you to a stop. Instead, what they do is they bleed off the kinetic energy to recharge the batteries. And because you're bleeding off kinetic energy, what has to happen to the car? It has to slow down. That's a law of physics. In fact, on the Tesla Roadster, I have read that they will tell you that the brakes will never need to be changed for the entire life of the car because it's only in the final couple of meters when you've lost almost all of your kinetic energy that friction is being used to stop the car. The rest of it is a system where they're actually bleeding off your kinetic energy and recharging the batteries. That's kind of nerdily cool. I want to find out how they do it because I've tried to visualize the mechanism. I need to go Google some Tesla Roadster specs or take one for a test drive. That would be so cool. Example 4. Way back at the beginning of the year, you may recall I did an RCMP question with you, but I had to fake it. I had to claim that the driver had his cell phone on and the cell phone had recorded the skid sound so that we had the variable time, because you may recall t was when we needed in almost every equation. Here's an actual accident. Here's actual investigation. RCMP officer is investigating an accident. The car has struck a pedestrian at a school crosswalk. There are no witnesses. The officer measures the coefficient of friction at the accident to be 0.65. There's various instruments that you can do to measure the coefficient of friction in the pavement. And with a tape measure, he measures the skid marks are 49 meters long. Should the RCMP press charges against the driver? We want to find initial speed. Here, I think we have enough information to figure out force of friction. What do I have that relates friction force and speed? Our new definition of work. Our new definition of work. Does this question mention there's a hill at all? No. By the way, if there was a hill, all we would do is we would calculate what the change in height was, and we could certainly include it in the equation. So if the crosswalk, if the school zone was on a hill, it's really not that much more difficult, because energy is a scalar. But yeah. What's changing anything? Are any of those zero? In fact, what's the final kinetic energy of any car accident? Always zero. I mean, they're not still moving, okay? Now, I'm going to have a negative here, because it's 0 minus, see the negative right there? But the friction is in the opposite direction. If it's okay, Natalia, I'm going to ditch the negative just for the rest of the question. I just want to find the magnitude of the speed. I know the car was traveling forwards. I can safely assume that. Okay? So this is going to be you'll notice I didn't write the W. How else can I write work? Cade, how else can I write work? You gave it to me on the last question too. Which force was bringing the car to a stop, Cade? There it is. This is the RCMP accident investigation equation. Now, they're a bit more accurate. There are a few more complicated things, because it turns out also as a car slows down, its center of mass shifts and the front end presses down, and that can also change this. And I'm sure they take that into account if they're pressing charges, but it starts here. What do we want to find? If the RCMP investigator wants to press charges or wants to know, what's he interested in? Amy, let's get that by itself. I think, look up, times by 2, same thing, yes? Divide by m, yes? And then, oh, Amy, how to get rid of a squared? Mr. Dueck, they didn't tell me the mass. Relax. Maybe if we're lucky, maybe it'll cancel later on. We'll find out. So what I have, and this is complicated enough that I think I'm going to rewrite it. V initial is going to be big square root of 2 friction times distance all over m. Okay. Big square root 2 friction. Oh! Friction is what times what? Mu. Don't write this down, just watch. Times the normal force times distance over m. I don't know the normal force. You know what? If we do a little free body diagram, I think we have gravity down, normal force up, friction. There is no forwards force. How do I know friction? Because the car was being brought to a stop, so it was decelerating. So there should be an unbalanced force that way. But here's the question. I don't know the normal force. Oh, but look. I don't know the force the same size as the normal force. Which one? Okay, so you can write this down, but then watch what's going to happen in the next line. It's going to be 2 mu mg times d all over m. Colin just got a little kind of half smile because he saw it. How many m's on top? How many m's on the bottom? Did I need to tell you the mass of the car? Now let's double check. Did they tell me the coefficient of friction? Did they tell me mu in the question? Yep. G, 9.8. Did they give me the distance? Yep. Oh. Okay. Plug and chug. And by the way, this is minimum speed because he might have stopped before skidding. He might have slowed down before skidding. So you could use this in a court of law to prove probably he was going or she was going faster. Usually say he because guys are stupider drivers than girls. Sorry, but it's true. What's mu? I don't know. What's mu with, what was mu? 0.65? It's about right for pavement. G, 9.8. 49 meter long skid. Oh, it's not over anything. Ha ha! Bottom cancel. That's kind of cool. I get almost exactly 25 meters per second. I'll call it 25. So, the initial speed. Let's put that to kilometers per hour because that's what school zones are measured in. How do I go to kilometers per hour? I seem to recall it had something to do with a 3.6, but I can't remember what. Times by 3.6 or divide by 3.6? Times. Oh! In a school zone. Okay. In fact, you know what? If the pedestrian that was struck, for example, passed away, this person will be charged with vehicular homicide. Like this is excessively fast, or at least manslaughter. If the person doesn't pass away, they're certainly though going to probably, they might even serve jail time. Certainly they'll lose their license and pay a hefty fine. And this is unimpeachable with that big a difference. And I made the numbers up pretty big, but with that big a difference, absolutely this driver would have no leg to stand on. Especially because, as I said, Noah, they might have slowed down before skidding. They might have hit the brakes, been slowing down, and then go, oh, good gosh, I'm going to hit somebody, and then hammered the brakes, and that's when the skid started. But they could have been going faster through the school zone. I like this question. I like this question. I like this. I think I've just decided I'm going to put a variation of this one on the test. What kind of a variation? I'll probably change the length of the skid, and I'll probably change the coefficient of friction. Okay, that's a nice application. We're going to finish with this motorcycle video. Put your pencils down. From the video, we have t equals 15 seconds. We have VI was 220 miles per hour. We'll do a conversion in a second. And we have VF equals 100 miles per hour. Any of you drive in the U.S.? My conversion factor, I know that in the U.S., 60 miles per hour is around 100 kilometers per hour. It's the freeway speed. They're within it's close. It's like 61.2. Anyways, so I'm going to go, I want miles per hour to cancel. I want kilometers per hour on top. So I guess I want the 100. I think to do the conversion to kilometers per hour, we want to go times by 100, divide by 60. Can you all do that for me, please? So what's VI in kilometers per hour? What's VF in kilometers per hour? First of all, let's do VI. It's going to be 220 times by 100, divide by 60. Now that's kilometers per hour. But what do we do our speed in? Oh, how do I go to meters per second? So divide by 3.6, 102 meters per second. That is a football field every second. Okay. V final is going to be 100 times 100 divided by 60. That's kilometers per hour. Divide by 3.6. 46.3. Okay. First thing I want to find out now is how much work did the brakes do? Well, work is going to be the change in potential and the change in kinetic. Right? You saw the road, Justin. Was there any hills in that road, or was it flat? Oh, so I think what you're saying, Justin, is, hey, Dueck. Right? And Justin, what's changing anything? You've got it. What's changing anything, remember? Something minus some. What is it? Come on, you can do it. Final. Yeah. And it's hard to say by every year. It's finest minus. It is tough to say. Final minus. So if I hear you correctly, kinetic energy final minus kinetic energy initial. That's what you're saying? Yeah. Are any of these zero? Was he ever stopped? No. Okay. A half mv final squared minus a half mv initial squared. All right. I did a Google search because in the video he did identify the motorcycle, and then I made a rough guess as to the rider. So let's assume total mass is 300 kilograms. We're rounding a bit, but we're close. So it's going to be a half times 300 times 102 squared minus a half times 300 times 46.3 squared. How many joules of energy were turned into heating up the brakes? Because that's how this thing was stopping.
Shouldn't it be 102 and 46.3
Be switched? Absolutely. Carson, you are totally right. Candy for you, Carson. 46 point. Now, thankfully, you'll get the same answer. It's just one's negative, one's positive. So sorry about that, folks. You're right. Totally. Because we're losing energy. We should get a negative answer. Let me get you your candy. Here you go. A half 346.3 squared minus a half 102 squared. Do you get, do you get that? Negative 1239 blah 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 blah. No? Yes? Yep. So negative 124. How about negative 1.24 times 10 to the 1, 2, 3, 4, 5, 6. Yeah, we got to go scientific notation. Negative 1.24 times 10 to the 6th joules of work. Now, some of that did go into sound because you could hear the sound pitch change, and sound is a form of energy. Most of it went into heat. Let's say all of it did. B. How many watts of power was generated there? Well, power is, what was the equation for power? Work over time. How much work? I'm going to ditch the negative. 1.24, because I know we're losing energy, times 10 to the 6th divided by, how much time did we say it took? 15 seconds. $82,600 watts. How long could you power a 60-watt bulb from that? Well, time is work. Sorry, let's do it this way. It's going to be 82,600 divided by 60 watts. Is that going to be time? That's going to tell me how many 60-watt bulbs I could light, Mr. Dueck. How can I get a time out of here? Well, let's divide it by 60 first of all. Divide it by 60. I could light, instead of T, let's call it a number sign. I could light, well, 1,380 bulbs. And 80 60-watt bulbs. There's a lot of energy there. That's why that regenerative braking that the hybrids do is pretty cool. May as well use that energy. I'm not going to get to the Nerf dart gun. Did I have questions here? I do, and I got a cool video. Lesson went a little longer than I planned. See if you can figure out number one. Number one is tricky. 2 is more straightforward. 3 is good. 4 is good. 5 is good. I haven't done one like that, but see if you can figure it out. Otherwise, I'll talk about it next class. 6 is good. 7 is good. So far, I've skipped, I think, so far, I skipped, which one? 2? Sorry, I skipped, did I skip any? Oh, well, that was mean of me. 1 is tricky, but I'll talk about it next class. You'll get some time Friday to work on this because we're doing a lab Friday, so you can get a head start. A couple of cool videos to show you.